Hello, and welcome to today's ACM Tech Talk. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of nearly 100,000 computing professionals and students. I'm Eric Meyer, Director of Engineering at Facebook, and before that, founder and CEO at Applied Duality. I'm also a member of ACM and the ACMQ editorial board. You can find more info on my background in the bio widget on your screen. For those of you who are unfamiliar with ACM or what it has to offer, here's some more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. You can see some of the highlights on your screen. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. ACM provides timely computing information published by ACM, including communications of the ACM and Q magazines, access to the ACM Digital Library, the world's most comprehensive database of computing literature, international conferences that draw leading experts on a broad spectrum of computing topics, support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Prize in Computing Awards, and the updated ACM Code of Ethics, a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions in professional practice. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you'll find some additional widgets and resources. If you're experiencing problems with the slides or audios, press the F5 key in Windows, Command+R if you're on a Mac, or refresh your browser on a mobile device. Or you can close and relaunch the presentation. To control volume, adjust the master volume on your computer. If you have questions during this talk, please type them in the Q&A box at any time and click the Submit button. I will organize the questions as Adam speaks, and he will reserve time at the end of the presentation to address all your questions or most of your questions. This session is being recorded and will be archived. You will receive an automatic email notification when it comes available. And check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you'll see a survey open on your screen. Please take a minute to fill out to help us improve our tech talks. You may also open the link to the survey at any time from the resources window on your screen. You can use the Facebook and Twitter widgets on the bottom panel to share the presentation link with your friends, as well as tweet comments and questions to the hashtag #ACMLearning. We'll be watching for your tweets. We also have a community discourse page to continue the discussion after this webcast, including questions we won't be able to get through the Q&A. Today's presentation is PyTorch, a modern library for machine learning by Adam Paszke. Adam is an author and maintainer of PyTorch. He has already worked with large organizations like Facebook, AI Research, Google, and NVIDIA, despite the fact that he's only recently graduated from the master's program in computer science at the University of Warsaw. Currently, he's also finishing his second major in mathematics. His general interests include graph theory, programming languages, numerical computing, and machine learning. Adam is also an ACM member. Adam, without further ado, take it away.
All right, thanks a lot, Eric. Okay, hopefully you'll be able to see my screen right now. If you can't, then please just let me know. But yeah, I think we can just go ahead and get started. So thanks everyone for coming. I'll be talking today, as you know, about PyTorch and sort of presented as, in the context as a library sort of for solving a lot of problems associated with machine learning. But ultimately, a lot of the things that I will be talking about today go much further than machine learning, and hopefully, you will see that they also apply in a significantly wider context as just machine learning. Yeah, as Eric said, I've been with PyTorch since the beginning, and so I'm one of the original authors, and I still try to contribute as much as I can. And yeah, I just wanted to take just a few seconds to sort of thank ACM for organizing this particular talk, and for Eric for moderating and choosing the questions. Anyway, so when you think about PyTorch, it's sort of a very wide term that you can think about, right? And you can organize it into essentially multiple layers, right? So it's sort of at the very core of all of it, and sort of the inner tier, there are the critical components that sort of implement the very fundamental functionality of the library, the like mathematical kernels, and also things like automatic differentiation. We'll be talking about all of those, so don't worry if like you don't fully get what I'm talking about right now. And then there's also a just-in-time compiler that I will also briefly talk about later. Then sort of as a second tier, this second tier is also included whenever you download PyTorch. You also get basically a bunch of utilities, which will help you develop the applications PyTorch is usually used for. So, there's the NN module, for example, which is used to build machine learning models. There's the Optim module for gradient-based optimizers. There's distributions for things like probabilistic programming, distributed computing helpers, multiprocessing helpers, things for quantizing your machine learning model to make them more efficient at inference time. And yeah, so PyTorch sort of there's sort of a very core on top of which everything is implemented, but it also comes sort of with some batteries included whenever you install it. And then there's like a whole ecosystem essentially of much more domain-specific packages, which then you can use to also simplify the implementation of some particular use cases. So, there are packages for things like audio models, there are packages for vision models, for text, packages for basically sort of secure distributed learning with encrypted data, for Bayesian approaches, for graph learning. So quantum computing, there's basically a whole long list of different packages you can try out, which are of really high quality. So you can see some of the examples in here, but of course this is not like a complete list. So if you think about PyTorch, you can really think about this. Obviously, we want to be good citizens in the Python ecosystem, so that's just sort of the ecosystem around PyTorch. But as you'll see, you should also be able to easily integrate whatever we provide with the rest of the Python packages, because there's just a lot of things out there. Yeah, and at the lowest level, PyTorch, if you think about it, the sort of the core component to PyTorch is pretty much the same as NumPy in many ways. Or if you've done any sort of data analysis, data processing in Python, then you have surely used NumPy. If you haven't really done this, then well, you probably know software packages like MATLAB. They all basically provide the same software abstraction, right? So the very core software abstraction they provide is a multidimensional array. Multidimensional array is like a generalization of a nested list, essentially, where at every single nesting level, all of the lists have the same length, right? So you can think of, a matrix is like a too deep list, sort of a twice deeply nested list, right? And similarly, then you can take a matrix and you can stack matrices and get like a cube of numbers, essentially getting like a 3-dimensional array now. And then you can take a stack of cubes and you get a 4-dimensional array, and so on, right? So this is exactly sort of the primary object and the primary abstraction that all of those packages provide. The benefit that they give you is that, for example, if you use Python, if you just were to represent the data as actual lists of lists, then it has two major downsides. One of them is that encoding even very simple operations becomes very difficult. And the other downside is that it's actually very inefficient. So NumPy, MATLAB, and PyTorch, they will store the data in a way which is basically very native in some sense to your computer, in which basically enables those libraries to do the math much more efficiently than like a completely general purpose sort of programming language, which does not have all of those abstractions built in, and then Python in particular doesn't have them built in. And sort of going back to the first issue, which is that, well, you would have to write out explicit for loops. The one benefit of this array, there's a whole domain-specific language, so like a DSL that's associated with those arrays, and that's like a DSL of mostly mathematical operations, right? So for example, And one of the benefits of this DSL is that essentially you don't ever need to, you pretty much never have to write loops in your programs, right? So in here, for example, the statement C equals A plus B essentially adds 2 to every single element of the array A, no matter how many elements there are. So like a lot of your code sort of has implicit for loops implemented sort of inside the operators that are used. But thanks to this, even though Python is not a very efficient programming language, even though it's not very fast, because those operations and those loops are sort of implemented in an efficient way, using probably some different languages as well, that you can basically get pretty much the peak performance on most of the workloads that you want to express. Of course, mathematical operations are not everything. Then, for example, the next statement, this D equals C, and then some indexing expression. This, for example, selects all of the rows. That's what the column means, and then the first and the third column of the array C, right? So, you can do mathematics, you can do basically selecting subsets of those arrays, you can check their shapes, which is sort of the extent in each dimension, and then also the number of dimensions. You can learn this from the shape as well. And then there's like a whole basically range of different mathematical, like statistical operations, like at the bottom, you have a matrix multiply and some sampling from the normal distribution. So there are hundreds of different operators on those arrays that sort of compose this like domain-specific language that you can use to implement your programs. And as I mentioned, at the very bottom, Torch is exactly the same. We don't necessarily call those things ND arrays like NumPy does. We just call them tensors. But most of the code stays exactly the same. Some of the names that we use are slightly different, mostly because of some legacy reasons. PyTorch did not come out of the void. I will talk a little bit about this at the very end of the talk. So for example, some of the names actually come from MATLAB instead of NumPy. But the general idea behind all of this is pretty much exactly the same. And yeah, just to sort of convince you that, well, you have NumPy and now you have PyTorch, and now it's the question that when you start a project, you just have to pick one or the other, and the answer is that you don't really have to do that. You can sort of pick and choose them based on whatever features you use, and we're really trying to make it very easy, right? So even if you have an existing project right now, like of course you can use PyTorch for like the new projects you might be developing, but even if you have a project that's existing that does something, you can still start integrating PyTorch step by step, which also enables you to have a smoother transition essentially, right? Like it's always easier if you can just like change the code function by function to do something slightly differently, except maybe implement it in a semantically the same way, and then you can, let's say, run the tests at every single step to verify that your code still does the same thing that it does, right? As opposed to just rewriting the whole code base using a completely different library and then just hoping that you don't make an error somewhere along the way, and then just spend days debugging the issues, because, well, debugging numerical programs is not very fun. And yeah, with Torch, you can essentially do that relatively easily, right? If you have a function that takes in some NumPy arrays and returns some NumPy function like at the top, there are functions like Torch as tensor and NumPy as array, which you can basically use to convert NumPy arrays into Torch tensors. And the benefit that you get from this is that those conversions are essentially free. Like there's no, even though the arrays may be huge, the cost is entirely constant. Actually, they actually share the data in memory. We use the same representation as NumPy, and so we can just reuse the memory that NumPy arrays actually use, just rewrapping them sort of in PyTorch objects such that you can actually pass them in to a PyTorch function. So both ways you can just sort of jump into the system and out of the system really cheaply, and so you can slowly start transitioning, let's say, a whole implementation like this. So you just sort of cast the inputs to PyTorch, let's say, rewrite the NumPy code to PyTorch code, and then cast the result back to NumPy before returning it. And the whole system, providing you actually implement the PyTorch code that does the same thing as the NumPy code, your whole system does not lose any performance, and it should just perform exactly the same thing. So, just to sort of calm you down, that it's not just like a framework which will wall you off and, will force you into a completely different ecosystem than everything you can benefit from in Python. But, obviously just re-implementing everything that NumPy already does would be kind of pointless. So obviously there's more. And really there are two crucial features, I think, to what PyTorch does. The first one is Accelerator support. So pretty much every single device that you use today has an accelerator of some sort. For a lot of numerical computing use cases, it turns out that it is GPUs, which have been developed, for example, for completely different applications than scientific computing, they actually excel in many machine learning workloads and also just high performance computing workloads. They turn out to be machines to which this array DSL maps perfectly, because there's a lot of parallelism in this array DSL. It's actually really easy to execute this on the accelerators. And so it's actually one of the easiest ways to program and to take advantage of the accelerators like this. And PyTorch in particular supports NVIDIA GPUs, AMD GPUs, and Google TPUs. But there will be probably support for more hardware as it comes out, but for now, those are sort of the three primary things. And really, accelerators are one of the reasons why sort of deep learning in particular could really take off, right? Like the 2012 breakthrough on ImageNet, that model was in particular trained on a GPU, and so we do try really hard to have very good support for all of those accelerators, because they can usually give you basically an order of magnitude improvement in a lot of the workloads that people encode using PyTorch. And the second component is high-performance automatic differentiation. So automatic differentiation is a technique which essentially lets you write a program and sort of you never have to compute the derivatives sort of by hand, right? So in the past, let's say if you just wanted to write out a function and then let's say get its gradient for the purpose of let's say optimization, right? You would maybe have to sit down with a piece of paper and figure out using the chain rule and the primitive differentiation formulas. What is the gradient? Then just code up the derivative code essentially in a completely separate function, right? Fortunately, differentiation is a completely mechanic procedure, and so a computer can do this for you, right? And so a long time ago, people have already figured out how to basically take pretty much an arbitrary program and compute a derivative out of this without you having to necessarily spend any time sort of figuring out what the derivative it is, right? Like as long as your program implements a differentiable function, the system should be able to efficiently and easily let you take the derivatives of the functions that you compute. And that's sort of the second basically important use case, let's say over NumPy, that PyTorch provides. And that's also really crucial for machine learning, right? Like the models that people actually develop these days are extremely complex. And so if you were to just sit down and try to work out the equations for the derivatives by hand, that would just be extremely complicated. And so this is also really one of the enabling factors that let the deep learning in particular, I think, take off in the recent years. And so, we have those features, but the question is, how do we actually expose them? And the answer is that we expose them in a way which is, I think, very familiar if you've ever used a library like NumPy. So in particular, the programs you implement using NumPy, they're very polymorphic in some way, right? So in this case, we have just a program which samples some parameters for a model we will be implementing, and the model is just this linear model function. So it's just like a defined transformation of the input. And then we can just sample some example input and try to evaluate the model on it, right? And so in some sense, this there's a lot of dynamism happening in this code, which is sort of not visible statically. You cannot just resolve it statically. And that's, for example, because there's an infinite number of different size configurations. You can evaluate the linear model function, right? This piece of code will work out for an infinite number of different shapes of weight. Of course, not every single configuration of sizes will be valid, because not every two matrices can be multiplied together, which is the operation we're doing in here. But there is still an infinite number of different sizes of matrices that you can multiply together, which you don't really specify in the code of the model that you implement, right? It's only specified in the place where you actually create the parameters or create the inputs when the sizes with which you will be evaluating the code are determined. And similarly, if you want to do mathematics on a computer, you also have to commit to a particular precision in which you will be computing, the quantities of interest, right? And so NumPy also similarly, with a single function for this linear model, you can also use the same code to basically evaluate this function for any particular precision, as long as you change the precision of the inputs. Sort of the precision of the intermediates will be automatically inferred from the precision of the inputs, right? And so, there's already a lot of polymorphism in this linear model code. Of course, in PyTorch, as I mentioned, the base is the same, so you can implement it basically in the same way. You can change shapes, you can change the data types. But now the question is, how do you actually use the accelerator support and automatic differentiation? And it turns out that both of those actually just extend this same framework, right? So for example, for accelerator support, you can see that the code of the linear model actually did not change at all, right? The only thing we have changed is when we are creating the inputs to the function and the parameters to that model, we just specify that they are supposed to be created on a particular device. And what this changes is that the actual data of those arrays will actually not be kept in the main memory of your computer, in the RAM memory, but actually in the global memory, in the RAM memory of the accelerator that are used. So for example, they will actually reside in the GPU memory. And it's also interesting because a lot of those decisions can be made at runtime. So with the line at the top, for example, this will actually pick the GPU if you have a GPU in your computer, but otherwise it will just fall back to the CPU. For example, enabling you to actually prototype on a less powerful device like a laptop, which may not have a GPU which is capable of accelerating those workloads. But once you put it on a server which actually does have a GPU, the script will automatically change to it, right? But the really important part of it, again, is that the code of the function you implement does not change. The only thing that you change is the metadata of the inputs, and then sort of the whole computation reorganizes itself around that decision. It works exactly almost the same for differentiation. So for differentiation, the only thing you have to change is, again, for the quantities, so the particular kind of differentiation that PyTorch supports, because it's the one that's really the most important for machine learning, is reverse mode automatic differentiation. And that's just really a fancy way of saying that we can differentiate scalar functions. Efficiently, we can differentiate scalar functions with respect to a lot of inputs, right? And that's usually the case you have in machine learning. You will have a lot of produce a single number, which essentially will tell you, it's usually like a loss function, which tells you how good or how well or how bad you actually did on a particular instance of a task that you were trying to solve, right? And you will be optimizing to let's say lower the loss, so lower the badness of it, make yourself better in some sense at this particular task. And it works similarly. So the way you actually use it in PyTorch is on the parameters of your model, you say that, well, they will require the gradient, right? So the derivative of a scalar function is usually called the gradient. And so if you say that different tensors will require gradient, that will basically turn on the automatic differentiation subsystem. By default, it's disabled because it takes some extra computational resources to actually do this efficiently. But so you have to explicitly opt into that feature. And so if you compute an output and if you compute some kind of a scalar loss, then you can just use a function, again, linear model. The code of the function that you compute stays exactly the same. And then you have this magical function that's called torch autograd grad, where you give it the scalar output of the function that you have just computed. And then you give it the sort of a list of inputs with respect to which you want to get the gradient. And it will just return you the list of the same length of tensors, the same shapes and devices and data types, which are the gradients of the quantities with respect to which you have differentiated. And the really important part in here is that linear model can contain, or the thing you differentiate, the function you differentiate, can essentially contain arbitrary Python code. There's no limit whatsoever to what particular implementation you use, as long as it's all different mathematically equivalent implementations will give you pretty much the same gradient up to some, let's say, maybe floating point differences sometime. But you can use, let's say, async await functions. You can use generators. You can basically go crazy with any particular Python language feature. And as long as the function that you have actually implemented is differentiable, we will give you the true gradients of that particular function. So there's really nothing that limits you. And basically, both of those features are them and start using it. As I've said, that's pretty much everything you need to do ML, right? So if you just want to use something like stochastic gradient descent, pretty much you have all the building components, right? If you have a data set of inputs and targets, and let's say that your model is parameterized by some vector theta, then you just iterate over the data sets and targets. You evaluate the model on for each sort of parameter, right? For each input, and you evaluate the model with the current set of parameters that you have derived. Then you get some output, you use the loss function to compare it to some target, you get back the loss that tells you how well you did, Then you take the gradient of the loss with respect to the parameters. That's the torch autograd grad line. And then you just, well, change the parameters, right? You sort of take a step in the space of all parameters to sort of optimize towards, making the loss smaller on this particular example. That's basically how pretty much most of supervised learning works, right? Of course, this is not really the easiest way to do this thing, right? So, for example, if you have a really complex model, just keeping all of the parameters in a single flat vector, that's probably a bad idea, right? So it might just be better to have like a better way to organize your model. And similarly, if you look at a lot of papers, you will often see some diagrams like the one on the left where, people, let's say, think of models as some kind of a hierarchical structure where you have those like boxes that encode different operations. And so you have, let's say a box in here that encodes a linear transformation and then another box that encodes something called the attention layer, essentially. And then you can also take those boxes and, like, let's say, throw in some extra additions and also group them in a bigger box, which is the gray box in this particular picture. And you will say that, well, okay, so now you can use this gray box, let's say, multiple times in your model as like an atomic unit of some kind of computation, right? So naturally, when you think about machine learning models, you often have this hierarchical structure. And those different boxes, like linear or attention, they can actually have different parameters. And so sort of transitively, the gray boxes also can have parameters because in some sense they're parameterized by everything the inner boxes are parameterized by. And yeah, and PyTorch also provides you some interface to actually deal with this, right? So the way you actually do this is there's a torch and package, which you usually import as just an n, and then there is a class which is called an n module. And so the way to implement, for example, this gray box that you see on the right of the screen here is to actually implement a subclass of an n module, and then you have to implement two functions, an initializer and then a forward function. So the initializer, essentially what it does is it builds up all of the sub-boxes, right? So all of the sub-boxes, and essentially you really only should be building up the sub-boxes which have parameters. So in this case, maybe the attention layer may have some parameters inside, and then also the linear transform also can have some parameters. So this is where we will construct it, and everything you do is you just assign it to an attribute of this class. And another important thing to note is that the initializer can have some arguments, right? So when you construct your models, there are some hyperparameters, like how many layers I will actually have, right? Or what kind of nonlinear function I will actually apply in between of some of my layers, right? And so for all of those, you can just take some extra arguments to your initialization function, which will specify like how your this like gray box may not always encode this particular structure, but it can also encode like a whole class of different structures that works like this, right? So in this particular case, the linear transform, for example, it is parameterized by how many input features it will have and how many output features it will have, right? So there's an infinite sort of number of different configurations of this gray box, depending on how many outputs you actually might want to have in the end after you compute it, right? And so that's the role of the initializer. The role of the forward function is to basically implement whatever this particular box does, right? Including the delegation to lower level boxes. So if you take this like graph, those arrows, so they sort of encode the data flow of different values throughout this function, right? So at the bottom, from the bottom comes in the input, right? And so what you do is you apply the attention layer to the input, and then you add it to the just original input. That's sort of this like skip arrow. And then you get a quantity, which, well, in this case, maybe we call prelinear. And then we do the same. We just apply a linear layer and then add it again, the prelinear to it, right? And then we get a result and we just return it. So this is sort of forward is the place where you actually translate this graphical structure into an actual model. All right, and what models that you do is you know when you create a model, you specify all of the hyperparameters. You have to actually give some numbers or some configuration parameters for them. But the benefit you get is that now you actually can access the hierarchical structure, right? So for example, if you do model.linear now, you just get the blue box from this graph on the right. Yeah, that's the only thing you get, right? And similarly, linear has a parameter called weight. Linear is like a defined transform. So you can do model.linear.weight, and you will just get a tensor which encode the one of the parameters of the linear layer, right? So it's not you have a flat vector and you have to slice off a particular range of indices. You just have them encoded as a completely different multidimensional arrays with potentially different data types, potentially being on different devices. All of this is legal. And another important thing that this gives you is that that's essentially an abstraction that lets you get easy access to parameters of your model, right? So all of NN modules, you can sort of think of them as partially applied functions. You will see a good example of that in a moment. But they're partially applied in the sense that they also know exactly to what sort of parameters they have been partially applied to. So you can say model.parameters, and that will just give you an iterator over every single parameter in your model. So in particular, model.linear.weight will be one of the things that would be returned or like yielded from the iteration over parameters, right? Similarly, you can say model.toCUDA, and that will take every single parameter in your model and just move it to a completely different device, right? So you can have thousands of tensors as parameters of your model, but this single call will like find all of them automatically for you and will just move them to a different device. You can print them, that's sometimes helpful, but it doesn't encode all of the information that's possible. And yeah, and so, the same loop looks very similarly using this abstraction. So, you again get some kind of a data set, you instantiate your model. In this case, we just take use the optimization package again. So that's optim.sgd, stochastic gradient descent, and we just pass in the model, right? And then we iterate over the data set, and we just, again, evaluate the model on every single input. Notice that now we don't pass in any parameters. The model like implicitly knows in which point in the parameter space it is right now. And this is what I mean by a partially applied function, right? If you've done any functional programming, it is as if the model has been partially applied to the parameters argument, and now is just a function from inputs to outputs. Yeah, and then you can, for example, call loss.backward, and what it does is it's very similar to something like torch autograd grad, except it's in some way much more convenient because it will just automatically find all of the parameters that you have used to compute this particular quantity. So in this case, that's loss, and for each one of them, the gradient will be accumulating into their .grad attribute. So if you say, for example, in this slide, model.linear.weight.grad, that will be the gradient of the last backward call that you've actually executed, and that will be the gradient with respect to the this like loss quantity that you differentiated in the last iteration of this loop. Then all you have to do to actually do the optimization is usually just do optimizer.step, and you can swap out different optimizers, and the code stays exactly the same. And then in the end, as I've mentioned, the gradients get actually accumulated into that grad attribute. So if you called loss.backward twice, all of the like .grad attributes would increase twice. Because you would just get the sum of the two of the same values. So it's also important to remember to call zero grad from time to time. Some algorithms will require this zeroing at different points, so it's not fully automatic, but that's essentially what's happening. All right, so that's sort of this is about the basic part of the library, and this is essentially how you would even go about implementing a machine learning model in PyTorch. And PyTorch really has been created to sort of facilitate rapid research and to make it really easy to express those models, right? But ultimately, like, it takes time to develop a model. It takes long iteration cycles, and so it's really important to be able to change your model quickly and validate your hypotheses quickly. But at some point, you will arrive at like a final product, like the resulting model that you're happy with, and at that point, something you might care about is actually taking it and deploying it to actually work in the real world, right? So, for example, give you some predictions for some particular use case that you have in mind. And this has been traditionally relatively hard with PyTorch, but we've put a lot of work into it, like over the last basically year or like a year and a half, and so it's improved greatly. And now I'll talk a bit about how you do this, right? So in PyTorch now we sort of talk about two different components, right? So there's PyTorch eager, and that's exactly the thing that I've been talking previously. That's sort of the NumPy-like API, and then there is PyTorch script, which is essentially a completely new programming language. But you should not be afraid of it because, as I'll show you, it's actually really easy to use. And if you know Python, you know TorchScript already. So PyTorch eager, the benefits of it are it's well known because that's just the NumPy way of doing things. It's easy to write and simple to debug because it just runs sort of as you execute the program, you just run the successive sort of mathematical operations. You can print the intermediate variables and all that. The downside is that it's really hard to optimize, right? In eager mode, we're just a regular Python library, so we sort of never know what kind of an operation will come next. And for some sequences of operations, if we knew that it will execute this sequence of operations, we could, let's say, execute them in a slightly better way, right? Because maybe there are some transformations we could apply that are sort of annoying to write out manually, so you might not necessarily want to do this by hand in your programs. but like a compiler hypothetically could rewrite them to make them faster. Similarly, there's a downside in that, well, if you want to take your model and if you want to, for example, package it and put it in a mobile app, if you just use the regular PyTorch code, which encodes the model as Python code, you cannot ship your mobile app without a Python interpreter. And Python interpreter is a really complex piece of software. It's relatively large. It's like in the tens of megabytes, essentially. So it will increase the size of your mobile app significantly in many cases, right? And it will also not run very quickly. So we would want to have a faster runtime that would let us execute those things on mobile easily and efficiently. And so this is exactly what TorchScript has been, why TorchScript has been created, essentially. So as I've said, it's a completely new programming language, but in some sense, if you program it, you will not even realize that in many cases, because it uses exactly the same syntax as Python, and it has exactly the same semantics as Python. So the benefits of it are that it's optimizable and exportable. So we can both find the array code that transforms the arrays in some ways, and we can actually export it to run completely without the Python interpreter. The caveat is that we use the same syntax and semantics, but it's not all of Python, right? So there are some Python constructs that will not be supported by TorchScript. Having said this, the range of constructs that are supported actually by TorchScript right now is really, really wide. And so for really the vast majority of use cases, that should just be sufficient. So, the real question is, okay, so we have this TorchScript thing, but how do we actually get to it, right? We have an eager program, we did some research, we developed some program. How do we get it to execute using TorchScript? And so we take this as an example. We take this not very machine learning specific function. And so if this is just a regular Python function, right? But the way to actually get it to work with TorchScript is you just add an annotation on top. And so this annotation, just TorchScript, what it does is it will tell us that you want to use, in this particular Python function, you just want to use TorchScript. And what we'll do is we'll inspect the source code, and like every time you execute this function, it will actually not run through the regular Python interpreter. It will run through like a custom runtime system that we've built to actually to optimize and execute this code. The important thing is that if this does not throw an error, then the program that looks like this and the program that looks like this, they're exactly the same semantically. There's no difference that you can notice except from, well, maybe some things may become faster, right? Because, well, we can optimize some things. But essentially, semantically, it should always give you exactly the same answers. Of course, when you sprinkle the TorchScript annotations, sometimes it will complain, and sometimes it will reject pieces of your code, saying that it doesn't support some of the features that are used. But if it doesn't throw an error like this, then it's 100% guaranteed to preserve all of the semantics of the user code. So you're just programming Python, and in some places you just add those TorchScript annotation, and everything magically sort of attempts to use the different runtime. But you can just think of it as if you're just programming Python. As long as like TorchScript is not complaining that you use a feature it doesn't support, it's all good. And the subset we support is relatively large. One notice that is important is that it's actually a statically typed language. So you need to provide type annotations on the inputs, but all the types of all the intermediates are actually inferred based on those. So there are some type annotations that you have to do in case of function inputs, but in the rest, you pretty much never have to actually annotate any intermediates with type information. We should be able to infer that. And what you can see on this slide is that like most of the built-in, for example, data structures like lists or dicts or optionals, they are already supported in TorchScript. And so if your program uses those, you can just like slap TorchScript on top of it, and it should be all good. And similarly, another thing you can do is you can actually implement whole classes. So TorchScript also supports classes. This is actually an example taken from a research project where you can see pretty much non-trivial and relatively convoluted Python code, but all of this is supported by TorchScript and sort of works out of the box. The only thing you have to do is add this TorchScript annotation at the top. The only sort of exception to this rule are NN modules, because TorchScript classes don't support inheritance right now. NN modules need inheritance because, well, your models will inherit from an NN module. So the way you use those is actually a little bit special. The way you script those is you instantiate the module, so you instantiate the model, right? And then you just pass it into the TorchScript as like just calling it as a regular function. And what you get back is a model which behaves exactly like the original model that you had in mind, but now it will also run through the like optimized runtime that we have built. Yeah, and you know, so again, getting back to the benefits that this gives you, you can export those things, right? So if you have a scripted function like add at the top in here, or if you have a scripted model just by, you know, passing in an instance of a model that you have just created, you can just call tortgit save on this object and specify a file name, and that will just dump all of the details, like all of the code and all of the parameters in case it's a model in this particular archive in this point. And what you can do later, for example, is there are basically sort of default workflows now, starting from version 1.3.0, which has been released this October. There are basically default sort of workflows for taking checkpoints like this and embedding them in both Android and iOS apps. So in some sense, you can just take your Python programs and just run them on mobile apps sort of through a different interpreter, which is, of course, in some sense geared towards executing code that focuses on those multidimensional arrays. It's not just meant to like accelerate any kind of Python code. So, you know, just a small caveat in here. It's really mostly geared towards things that are, you know, in some sense do some numerical computation. Yeah, and you know, it's also, just to like give you a quick note, the actual archives that are produced, they're just zip files with a relatively readable structure. You can even like unzip an archive like this, and there's a code directory, and you can just see all of the code that like the whole implementation of your model or of your function sort of printed out in a human readable format. You can even modify it and rezip it again. And that will just be like, you will just get a different checkpoint with like a different semantics in some way. So you can even easily inspect those checkpoints after you have actually produced them. And you can also alter them if that's something you really want. And yeah, and you know, it's not just for mobile. Like starting from 1.0, I think, we actually provide also like just a pure C++ library, which you can use to evaluate those checkpoints as well, right? So if you just link this library to your project, you can just do tortgit load, giving a path to the checkpoint. Then you can create, you know, some input, and then like as a one-liner, you can basically evaluate the functions on the inputs you created back answers, right? So pretty much anywhere where C++ can be, PyTorch, you can also use PyTorch and use also exported Python programs in those places. And also as a side note, starting from 1.0, we also provide a pure C++ interface. So everything, all of the APIs that you just saw in Python, they're pretty much one-to-one in correspondence with C++ APIs. So if your project for some reason calls for C++, like, I don't know, you're interfacing with a game engine maybe, and game engines are usually in C++, so maybe just adding Python to your project might be annoying, you can just use C++ to implement this, right? And in this way, you can also get rid of some limitations of Python, like, you know, the global interpreter lock, if that's really what's slowing you down. So I will not be showing a lot of examples for this, just to sort of give you an idea that it's really pretty much the same, except for some syntactic differences in your models. So this is an example of a Python model, and if you were to implement it in C++, it would look like this. So, you know, if I switch back and forth, it's pretty much the syntax is slightly different, but the lines are pretty much one-to-one with like how you actually describe things, right? So once you know one API, it's really easy to actually learn the other one. Similarly, pretty much all of the helpers that we have in Python land, so in here you see an example training loop. In C++, the same training loop would look like this. So again, like pretty much one-to-one, abstractions are exactly the same. It's just the syntactic differences between the different languages, but the overall code that you implement is really easy. It's really easy to do. There are no templates involved, so compiler error messages should be readable, yeah, it should hopefully work out relatively nicely. Yeah, one interesting component that I didn't have time to talk about today is the whole data loading pipeline, which we also provide as part of the data package, both in C++ and in Python. It's the second line in both of those examples. Yeah, and you know, as I mentioned, most of the packages like the neural network library, which also comes pre-built with a lot of those NN modules built in. They're both in Python and C++. The Optim package is there. The data loading package is there. The serialization utilities. There are some utilities to exchange data between C++ and Python programs, so you can actually mix both languages in a single project really easily. And then there's also the JIT namespace, which gives you access to this just-in-time optimizing compiler to execute the models that you have likely authored in Python. Yeah, okay. So that was a lot of sort of content about using the JIT as a mean of exporting the code that you wrote in Python, maybe as a result of some research project, and getting it into an environment which cannot really work with Python for some reason. But I have not talked all that much about optimization yet. So just to sort of touch the optimization aspect of it, we have definitely spent more time optimizing for actually making it easy to like support a large language subset than actually building out the full optimization pipeline for script. But one of the use cases we have actually looked at are recurrent neural networks. So recurrent neural networks are models that the rough outline looks like this. So you have some kind of a function, which, and here I omit for simplicity, which is called a cell. And then you have essentially the whole model is like takes a sequence of inputs usually to a sequence of outputs. And it uses the cell function to which is applied to a step at every input and to some particular state, right? And so the cell is like a function which takes the input at a current step and a input state and produces an output for this particular step and a state for the next time step, right? And then you can imagine just passing in as you progress over the input sequence, you also progress sort of over the states that the model is producing. So in some sense, it gets some kind of, let's say, memory or some kind of context about the inputs that it has seen in the past. So those kinds of models are, for example, useful for things like translation or things like that, or just text. And if you just take this function, right? If you just add this, you can notice that really the only thing you have to do to get it work with script is just add the annotation on the LSTM function. The LSTM cell function is scripted automatically just by the means of it being sort of used from the body of LSTM. Like if you call LSTM cell directly, this will not go through Torch script. But if you just call LSTM, the actual call to LSTM cell will be replaced like a call to an optimized version of LSTM cell, which will also use Torch script. And you can actually get some pretty nice results. So if you just use eager mode, if you just use the code that looks like this, it will take on some, particular input size. Of course, those are not representative, and the speed up that I show you here is not necessarily representative of every single use case. But the speed up you can essentially get is in eager mode. Let's say it takes 23 milliseconds to actually evaluate this model over some particular sequence, right? You can compare this to cuDNN. cuDNN is like a handwritten library by NVIDIA, where they basically provide handwritten kernels for many different kinds of very popular machine learning models. And so one of them is for an LSTM recurrent neural network. And so you can see that it's pretty much 4 times to up to 5 times faster if you just use the handwritten kernel than just the regular array-based code like in here. But just adding this Torch script annotation basically lets you bring down those 23 milliseconds to somewhere around 6 milliseconds. So that's pretty much a 4x speed up. You're staying much closer to the handwritten kernel regime in this case than to the eager mode regime, right? And so you might wonder, why is this important, right? If we have a handwritten kernel for this model, then why is it impressive that we can get a slightly worse performance than the handwritten kernel, right? And the real reason why you want to be able to do that is cuDNN only has a finite number of kernels implemented, right? So if you're doing research on some, let's say you want to play around with what this cell function computes. If you just change the cell function slightly, there's no longer a cuDNN implementation that will compute it for you, right? But the JIT is more general. It can actually take a lot of different cell functions that you implement, and hopefully it should be equally good at optimizing them as it is good at optimizing this particular case. So in some sense, it is applying all of those things automatically. So making the code much more convoluted, but it doesn't matter because it's an automatic tool. So you yourself does not have to go through the optimization process, but it allows you to experiment with models with which you normally, let's say, might not want to experiment because it takes a huge toll on your basically time budget for research if it slows you down, let's say 5x. All right, so I have just a couple of points to touch upon before we finish because we're running out of time. So PyTorch did not come out of nowhere. It's actually a synthesis of different packages like Torch 7. There's been 7 Torch packages before this, HIPS, Autograd, and Chainer. We initially took a lot of inspiration from other packages as well. We're very much community-oriented. All of the development is happening on GitHub through issues, pull requests. You can also be involved. You can comment. You can submit your own patches. We're very happy to accept more people. developer velocity is critical to us, to the point that in some cases it's more important than performance. We're not really aiming to like top every single performance benchmark. It's really more important for us that it's actually a system that is pleasant to use. But of course, we don't want to like sacrifice, let's say, orders of magnitude of performance if we don't have to in particular. We do focus very much on building composable abstractions. We really want to make the abstractions we use sort of easy to use, and also we want them to behave well when you compose multiple of them. And also, especially, we want to be able to give you the ability to actually pick and choose the abstractions you use. So in particular, we don't want to be a framework which like forces your problem into a particular way of thinking about it. We just want to provide you with tools to actually express whatever you want, and the tools that you use, which we have provided, should behave like in a very predictable way in particular, right? So that they should not surprise you all that often. Also close integration with other libraries is really important for us. I sort of touched upon this when I talked about NumPy integration, but there is also integration with things like QPy, so that's sort of like NumPy but on GPUs. We also work with authors of those libraries to enable easy sort of exchange of data between those libraries too. And as I've mentioned, a lot of the features that I talked about today, so things like accelerator support and automatic differentiation, they're not only useful for machine learning. There's a lot of other domains like physics simulations or finance, which actually might benefit from having access to those things too, right? Like NumPy is great, and NumPy is used for a lot of different things, in particular, not so much for machine learning, but it is used a lot for other use cases. And pretty much every single of those use cases, it can benefit in many cases from having access to an accelerator. So it might be interesting. I would actually be very interested in expanding the scope of PyTorch to other domains as well. All right, so that's almost everything I have for today. So I just wanted to take a moment to thank all of the sort of organizations that are supporting PyTorch, and also to all of the contributors. It is very much, as I mentioned, we're very community focused, and we do care a lot about the contributors to our project. So that's just a quick way of saying thank you to the long list of people who have contributed to it over all this time. And thanks for joining us. That's everything I have for today. And if you have any questions, I'm happy to take them now.
All right, thank you, Adam. Let's move on to the questions and answers. So the first question, there's quite a few questions, but I'll pick some, and see how much we can get through in the remaining time. Yeah. Here's one question. What does it take to add support for new accelerators, such as an FPGA-based circuit?
Right, that's a good question. So right now, it's not trivial for sure. And it usually, right now, it requires some modifications basically to the code base. So in some sense, you would have to fork the code base in some sense if you want to do that, which is not, it's not something that I'm very happy about. And we are sort of moving slowly to decouple. Like, we basically have like a hard-coded set of devices right now, and it's not a place where we want to be. So we are working to resolve this. But for now, it's not like, oh, you just implement like some interface and it magically works, even though the end goal is to have it work like this.
All right, thanks. So a kind of similar question is, what decides if a component of Python is supported by Torch script?
Well, it's mostly like there's no like fixed decision process. It's like, we try to look for the idioms, I guess, and for the constructs that people usually use when they're trying to use Torch script, or if we get, sometimes we get bug reports from people who are saying like, look, it would probably make sense to include this particular Python construct, and then we just try to make a decision just deciding if this falls in scope or out of scope, let's say, for now. In many cases, most of those constructs are relatively regular and should not be very difficult to support. So it sometimes just takes some time to actually implement this support. But for most of them, we should be relatively open to actually adding them.
All right, so here's another question that's similar to the first one. So is PyTorch available on Google TPUs?
Yeah, from what I know, you can use the TPUs that are in the cloud with PyTorch. There is, if you go to github.com/PyTorch/XLA, That's the repository where the TPU support lives. And it essentially goes through XLA, which is like a piece of software Google provides for interfacing with TPUs, and you can just use this. And it works similarly to GPU and CPU support. You just change the device. Instead of saying CUDA or CPU, you just say XLA, and that will move it. That will move all the tensors to a TPU, and if you run them through your code, they will actually execute on the TPU. I'm pretty sure that the images that are available on Google Cloud, if you actually spin up some instances, they may already have the TPU support built in, so they should be relatively easy to use. I'm pretty sure some people at Google have worked on that.
Thank you. So here's another one. It's a low-level one. So do you have any tips on profiling PyTorch code? So there's torch.util.bottleneck and NVVP or line profiler in Python. So how do you kind of pick between these different tools?
Yeah, that's a very good question. I think it really depends on. It's not always easy to It's very hard to have a single tool which does everything you need for your solves all of your profiling needs. So I would say that torch.util's bottleneck is actually a good sort of starting point if you just want to explore what your model, let's say, is doing, and maybe you will get some potential insights. But it is also a sort of program which, in some sense, tries to summarize and just automatically figure out things, which means it's not super smart. So it can also give you some not very valuable insights. If you just want to figure out if you're, let's say, CPU bound. There are different sort of ways of PyTorch code being slow, right? So in some ways, your PyTorch code can be slow because, well, the operations you execute are really expensive, and if you run them on a GPU, it just takes a long time to run them on the GPU, right? Similarly, it can be slow because you're running a lot of small operations. So even though they're really quick to run on the GPU, the cost of the cost of communication between the CPU and GPU is large enough that it's actually CPU doing most of the job, and not most of the job is just the communication part and not the computation part. And those are really the two important answers that you have to get. So what I usually do is I use sort of a cross of the NVIDIA profiler. If I use an NVIDIA GPU, I will use the NVIDIA profiler to see a GPU timeline. If it's actually packed with mathematical kernels, then that's a good sign that, well, you should probably spend some time optimizing your program, or I don't know, worst case scenario is you write some custom kernels maybe. But do keep in mind that the NVIDIA profiler will slow down your program a little bit. So if there are gaps in the program, if they are relatively small, then this means that it's probably just the profiler overhead. If they're really large, then this means that you're probably bound by the CPU-GPU communication. And in this case, it's probably better to use, we have torch.autograd.profiler, which is a very low overhead profiler, which lets you build up timelines of operations, but not necessarily without actually looking into what the accelerators are doing, which adds up to a lot of profiler overhead. So it's not maybe a super satisfying answer, but it really depends on the use case, and that's what I usually do.
All right. Next question. Is automatic differentiation implemented for complex numbers and complex activation functions?
Yeah, that's another good question. So complex support does not work great right now. There have been a few attempts from people sort of outside of the core team to actually add complex number support. And with some of the pull requests that have landed recently, it should actually be a lot easier to start adding it. So it does not work great right now. And I really want to get complex number support because that's, for example, what's blocking, let's say, some physics use cases to actually use PyTorch. But yeah, I mean, once we clear out those, that should be a lot better. So again, that's another thing which is not working great right now, but I would think that hopefully they should be implemented in a relatively near future as well.
All right, I think we have time for one last question. So let me pick this one. where do you start to become a contributor to PyTorch? For example, is there a Slack community that you can join, or how do people get involved?
Right. Yeah, I now don't remember if we actually have. So I know that a lot of projects actually do something like if you go to their issue pages, they will have labels with like good first issue. I don't actually remember if we're doing that right now. But something that I would recommend is go through even if the labels are not there, just go through the issues. Look if something like looks relatively approachable to you. If something does not necessarily look approachable and you have some, you might want to do this, but you need some extra context, you can also comment on the issue and someone will get back to you and hopefully give you some additional information for how would you go about solving this, or at least give you some code pointers for like where you should look, or like a pull request, which was doing something similar. So maybe you can follow similar steps. And also if you have any issues, we have very active user forums, which, are slightly more oriented towards the use cases and not necessarily hacking on and improving PyTorch. But there are a lot of people who know and understand deeply how PyTorch works. So you can also ask the questions there and hopefully someone will be able to help you.
All right. Well, that was it. I'm afraid we have run out of time today. I would like to thank Adam again for his great presentation and insightful answers to the many questions. And special thanks to each of you for taking the time today to attend and participate. Please remember the talk was recorded and will be available online in a few days at learning.acm.org. And you can find announcement on upcoming talks and other ACM activities at learning.acm.org and acm.org. Also, please fill out our survey where you can suggest future topics or speakers, which you should see on your screen right now. On behalf of the ACM, Adam Paszke, and myself, Eric Meyer, thanks again for joining us, and I hope you will join us again in the future. This concludes today's talk.